In this lecture, we're going to be reviewing the main aspects of IR spectroscopy, and we're going to do some examples showing you the strategy of how to solve problems. So here we have the main things that we want to highlight is where are the bands, weight, number, intensity, and shape. So to show you this is an important band here. Later we're going to see that that belongs to an alcohol. And we need to be learning how or reviewing how do we read the spectrum, the regions that we're interested in. So that's what we're doing, and then applying that to problems. So where is my next slide? Yeah. Okay, so here when you saw the previous picture, I had made a line. So, and that line was at about 1500. And that's essentially what separates what we want to be studying, which is here with the functional groups are. That is the diagnostic region. And this is like what we call the fingerprint. So no, we're not going to be using that too much, but rather this region. I want you to see that essentially all of the hydrogens attached to any atom, being nitrogen, oxygen, or carbon of different hybridization, these are going to be showing above 2800. So, but typically when I am analyzing a spectrum, I draw a line, say that is roughly 3000 centimeters -1, and this is 1500, and that's where I draw my line. So I'm going to be looking about that, and all of the H's bonded to something are going to be around or a little lower or above 3000. That's what we're doing. And these are important shapes that is important that you remember. You're going to have charts, but still you need to know shapes. Notice that this is highlighting hydrogens. So the hydrogen in a carboxylic acid, so that's very wide band. And notice that it's centered about this line, about 32 or so, or 30. But it is wide, and sometimes that covers other bands. So now here you have the alcohols band. Again, these are hydrogens attached to something. And here you have hydrogen attached to nitrogen. In this case, notice this is a secondary amine. Secondary amine, if this is ammonia, the secondary amine, you will replace 2 of the H's by R group. So you only have one stretch NH, so that's why you see only one band like that. But when you have the primary amine, you have here 2 H's. Because of that, you see these 2 peaks. Now, the other bands that we see here are hydrogens attached to different type of carbon. In this here, you see this is carbon, this one right here, just under 3000. We're going to be looking at carbon sp3 hydrogen. So right under, that's why I say that we want to be drawing the line right on the 3000. Well, that's not straight, but you can imagine that. So right under is carbon sp3. Right above here is a carbon sp2. So those are shapes that we want to know. And this is even higher. This is your carbon sp. And here we have other bands that are actually not with hydrogen. So all of these are marked before with hydrogens. Now this is carbon-carbon triple bond, carbon-carbon double bond. So important here that, for example, when you go to double bonds and you analyze carbon-carbon double bond is less intense than carbon-oxygen double bond. Remember that this has to do with dipole moment. The higher the dipole moment, the more intense the band is. The band with alkenes may disappear if this is substituted symmetrically. Said that if you have 4 groups the same, then that band will disappear. So pay attention to that. But it's sharp, but not as intense as the carbonyl. The carbonyl can be wider. The alkyne is also sharp and not as long. Here I want to point out that it's not here in this slide, but in the same region you will have the nitriles. But because this is a polar bond, this bond is actually stronger, so it would be like here, stronger, a little higher than carbon-carbon triple bond. This is carbon oxygen, and this is in the fingerprint region, so we're not going to be looking to that much. This peak I need you to remember. This is what differentiates an aldehyde and a ketone. Remember that in aldehydes we have this, and this is a ketone in general. So both these two will have the around 1700 centimeters -1, but aldehydes only will have these other say sharp peak, and this is in about 2800. That is what lets you differentiate between aldehydes and ketones. Okay, these are shapes that we want to remember. The chart you're going to have. These are the lines that I told you. So draw your line in 3000 and see you here right under. This is your alkane, so carbon sp3 hydrogen. This is right above your line of the 300. This is carbon sp2 hybridized. So hydrogen is of alkenes, and this is alkyne. So a little bit higher and sharper. So these are the, again, the weight numbers, but you guys have that on charts. Now here, if you were to predict weight numbers in what is that we should observe in regard to functional group. This is an alkene. And so that double bond, remember, this is at about 1600 centimeters -1. And it will show because it's not all symmetrically substituted. Here you have this. And plus this here is carbon sp2 hydrogen. So this will be this vibration particularly. This is about 3100 centimeters -1. Everything else, this is carbon sp3, carbon sp3, carbon sp3 hydrogen. So those are about 2800. Here, this alkene band may show, but maybe a little weaker, is a lot more substituted. And here, what's important is that this is lost. We no longer have an H attached to an sp2 carbon. So between these two molecules, this band will differentiate the two alkenes. Lastly, in the last molecule, we have an alkyne. So this is higher than that, but here we don't have hydrogens. Remember, if you see a line, that's a CH3. So it's lacking, it's not a terminal alkyne. Terminal alkynes will have this vibration, about say 3300 or so. But point is that in this case, we don't have it because that's a carbon. But you will have the carbon-carbon triple bond and the carbon-carbon double bond. That, again, may be weak. And the fact that you observe this or not depends on the degree of substitution. For example, if here you have metal and metal, then this band likely will not show up because of symmetry and cancellation of dipole moment. And in the case of an alkene like that, with 4 metals also, the carbon-carbon bond vibration will be lost. Okay, these are carbonyls. All we need to remember here is that all carbonyls, so being from an ester, that's a conjugated ester, ketone, conjugated ketone, ketone, they are in about the same range, so 1700. But of course, when you have the molecular formula, we will know if we have another oxygen, and here you will know if you have a carbon carbon double bond. So other things that you can identify in the molecule. Here, this is what I was mentioning about bands and related intensity with dipole moment. And the greater dipole here is what is explaining why the carbonyl band is so much more intense. And remember, in regards to intensity, that this graph, this is 100% transmittance above and 0 transmittance. So the light that is transmitted, meaning 0 transmitting is 100 absorption. So this is what we call this absorption bands, because essentially all of that is absorbed. Notice it's close to the 0 here. And again, this is not as polar, so not as strong. The width of the band is also important. And particularly when we have OH, this happens because remember that in the fluid, these are forming and breaking constantly, so new bonds form. So what you see really is an average here. That's why you observe a broad signal. Now, you can observe OH as sharp signal if you have a, say, diluted alcohol solution. In that case, not much chance for hydrogen bonding, and you may see that. Also, I have seen a spectrum in which you have, say, sharp and broad. So both things may be observed. The narrow for 3, say, no hydrogen bond associated in the associated. So here, this is a typical thing, spectrum of a carboxylic acid. Carboxylic acids are like that because very broad. These can form dimers. That is a dimer, so 2 molecules getting together. And what do we have? A carbonyl, that's this one here. And you have the OH, very wide. And the other peaks that we have here is likely to be carbon sp3 hydrogen, but it's pretty much covering that. Okay. Sorry, I can't talk right now. I'll call you back. I might have to edit that. I don't know. Okay, so let's continue here. And other shapes that we need to be remembering. These are particularly important. That means, notice where they are. These are at about 3,300, same. And notice, again, ammonia is like that, so 3 H's. In the primary amine, you replace one of the H by an alkyl group or aryl. But in any case, you have 2 H's. That's why you have 2 peaks in that region. And typically, you have like a shorter leg, if you will. And if you have a secondary, it's always 1. If you have a tertiary amine, then this is lost. So in your molecular formula, if you see a nitrogen and nothing here, you should be suspecting tertiary or other functional groups as nitriles, maybe. And you can also even have nitro groups or other things. But amines would be in that region, and you can immediately identify primary and secondary amines by that shape. Again, important to remember shapes. And here again, that's the line that you should be drawing. 300, right under is alkanes, right above alkenes, alkynes, and then amines and OHs. And remembering the shapes here to help you diagnose that. Here, we have how do we calculate the degree of unsaturation? When you have your molecular formula, it is important that we learn how to do that in an alkane. Notice the formula of an alkane is CnH2n plus 2, so C5, that will be twice is 10 plus 2 is 12, so that is a saturated compound, alkenes. And when you have saturated, okay, so if you have a double bond, now you have what we call 1 unsaturation. Then you can see here a difference of 2 H's. And also we say this is a hydrogen deficiency index equal 1. So 1 means 1 molecule of hydrogen, and that is 2 H's. In the alkyne, you have 4 fewer hydrogens. And here notice that the cyclopentane is like pentene. So this is also, these 2 are constitutional isomers. So same molecular formula, atoms are connected in a different way. Notice this is also C5H10. What that means is that one cyclic structure counts as a double bond. So 1 unsaturation. Okay, so we see here several combinations of having unsaturation. So again, 1 degree of unsaturation is like 1 mole of hydrogen, so 1 unit. So it counts at 1. And so here, possible combination. Here is 2 pi bonds, right? 2 pi bonds. And these are conjugated, and this is accumulated, but anyhow, is a dying. So 2 pi bonds, 2 unsaturation. Here you have in the triple bond, 1 sigma bond and 2 pi bonds. So 2 unsaturations. That is an internal alkyne and a terminal alkyne. So same. Here, 2 rings is 1 unsaturation per ring, so it's 2 unsaturation. Here you have 1 ring is 1 unsaturation and 1 for the double bond, so it's 2 unsaturations total. Here, 1 ring and 1 double bond, 2 unsaturations. Same here, double bond, ring, double bond, ring. And the general formula to calculate the hydrogen deficiency indexes, this formula we need to remember. So it's 1/2. This is twice the number of carbon plus 2 plus N is the number of nitrogen. Subtract the number of H's and subtract the number of halides. All right. Now let's start solving problems given that. So we have this molecule. This is a 5H10O. And if you see this HDI, that's the first step you always do, is 1/2. So 2 times the number of carbon, that's 10, plus 2, minus 10. Oxygen, do not count. So that is 2 divided by 2 is 1 unsaturation. Remember that that 1 unsaturation could be a pi bond or a ring. So with that, let's go to what we observe here. In regards to functional group, this peak is typical of OH. So we're going to say is something like that. But I need to look for a molecule that has an OH and has 1 unsaturation. So here, we don't have an OH, so I'm going to cross that. That is a carbonyl. It does have 1 unsaturation, but it's not an alcohol. Here, you have a cyclic structure, so it has 1 unsaturation, but no OH, so I'm crossing that. Here again, 1 unsaturation, but no OH. Here you have a 1 OH, so that's good, but we don't have an unsaturation, so I'm crossing that. Your only option is the last one, because you have the OH, which you have identified here, and you have 1 unsaturation. Now, there's a structure here, C6H12. So again, when you have the molecular formula, start here. HDI, so 1/2 of twice the number of carbons, so that will be 12 plus 2 minus 12. Oxygen doesn't count, that goes, so that is 1 unsaturation. And what you see here is all of those is right under 3000, and I have these intense band, and this is in precisely 1700. So notice this is 20, 19, 18, 1700. That is typical of a carbonyl bond. And so we have these elements. So we have 1 unsaturation in 1 carbonyl. So putting that together, I don't have a carbonyl here, so I'm going to cross that. That doesn't have an unsaturation and no carbonyl, so I'm crossing that. This molecule does have a carbonyl, but it has 2 unsaturations, because it has a cyclic structure. This one has what I need, so the unsaturation and double bond, this is an OH, so my answer is D in this case. Okay, moving on. Here, another molecule, C6H14, so this is 0 unsaturations. If we see this is HDI equal 1/2 of twice the number of carbon, that will be 12 plus 2 minus 14, that is 0. So I cannot have any of that. I don't have a carbonyl. Notice nothing here in 1700. And all I have here is a lot of under 3000. So this is carbon sp3H's. And so not having an OH, so no OH, no carbonyl. So I don't have that. I don't have that. No carbonyl. I determined that I didn't have unsaturation, so I crossed that. My only answer is the ether. So notice that essentially going crossing things that are not possible. Okay, so here we have fewer carbons. So HDI again is always your first step when you have the molecular formula. So 1/2 twice the number of carbons. So that's 8 plus 2 minus 8. Oxygen don't count. So that is 1 unsaturation. In here I have the big carbonyl band. Notice that I have 2 oxygens. So I have this, and that's for sure. And also I see this big band, that's OH associated. So all of that is consistent with a carboxylic acid. This is an ester. So I don't have that, so I'm crossing it. This is a carboxylic acid. That is a cyclic ester. A cyclic ester. That is, we call those lactone. This has an alcohol and a ketone separate, but this is typical, this shape of a carboxylic acid. This has 2 oxygen and 1 saturation, but it doesn't have a carbonyl. So after all of that analysis, this is 1, 2, 3, 4, so butanoic acid. It's funny that in this problem it says like it smells like vomit. That's absolutely true. A terrible smell of that acid. Okay, so now we need to choose on the spectrum. Again, we're trying to match here. So what do I have here? Can we say that we have a carbonyl? That is first question here. We don't. So I'm gonna cross this one. Also because that is a carboxylic acid. I'm not giving the molecular formula, but this structure is a primary amine. And I don't see like the double peaks that I should be seeing in this region. So not a primary amine, so I'm going to cross that. I don't have a carbonyl, so I'm going to cross that one. Also don't have an OH. I'm crossing that one. So, and I have these 2 choices. But I see here that this small peak here belongs to carbon sp2H. So here, when you have an alkane, we don't have those signals. Alkane. So this is indicative of an alkene. Alkene, okay. So that's your answer. This is the molecule that has that spectrum. Okay? Also, I forgot to say, this is carbon double bond. And this is not symmetrically substituted, so it has some dipole. That's why the peak shows. Okay, now another picture is the same compounds, but what do we see here? We see a carbonyl bound. All right, so it's got to be some carbonyl compound. I'm crossing the amine, not a carboxylic acid. The carboxylic acid should have let me do another color. The carboxylic acid has like this, very wide, so I'm crossing that. Does not exist, not an OH. And here I see a carbonyl. So what else has a carbonyl? This compound. So that's your solution. That's alkane. Okay. Moving on here. What I have that is significant. Nothing in 1700, so no carbonyl, not a carbon-carbon double bond. So no carbon-carbon double bond, no carbonyl, no OH, not an amino group, so this is it. So only carbon sp3H. That's what we have here. All right. Let's keep moving on that. So what is interesting here, the most remarkable thing is that we have an OH. So some ROH. So I don't have an amino. This is an ester, so no OH. That's not the typical shape of the carboxylic acid. When you have a carboxylic acid, typically the band, I'm going to use a different color, is so broad that it may go over that. So that's not a carboxylic acid, and carboxylic acid would have a carbonyl. So that's why I'm crossing this one. And so not an alkane or an alkene, so my solution is this. Again, because we have the alcohol band, we don't have a carbonyl. Okay, what else? Now, same series of molecules. Now notice this has this big broad band, and that goes even above all of the carbon sp3Hs, so that is your carboxylic acid. Also notice that you have the carbonyl band. Okay, so it's the same series of molecules, but all different spectrum here. Okay, what is interesting to see here? Again, you're looking for functional groups when you're looking at an higher spectrum, and that is about the 1500. In here, I have the shape. So it's not as evident, but typically that is a primary amine. Always is like this, two peaks. So that is your answer right there. We don't have a carbonyl. And all of the other peaks here are due to carbon sp3Hs. That's that. Okay. Now here another use of IR spectroscopy is say how we can monitor reactions. So what happens, what do you observe at the beginning and what you have at the left? So this is an oxidation and this is Jones reagent that is making chromic acid. And again, you see the primary alcohol is going to be carboxylic acid. So here I should be saying an OH, so the OH band should disappear and the carboxylic acid should appear. So disappearance of, well, the OH, and so it gotta be this one, because this is appearance, so this should disappear, the alcohol. And then I should have a carbonyl, so appearance, that appearance, and I should have this appearance as well. So I would say the most significant changes is that, because still the OH of the carboxylic acid is much broader, wider signal. So this is how you can tell that that reaction had happened. We do that in the lab typically. Again, you take the IR at the beginning of the reaction and then at the end. Here, that's another oxidation. Oh, I think I repeated the same slide. Yeah. Okay, moving on. So what do I have here? Carbonyl, so that's not moving, right? Lindlar's catalyst, this is to do a partial reduction of the alkene, and it produces the cis alkene from the alkyne. So you're adding two H's. What you should see that the band of the alkyne disappears and the alkene appears. So where is the alkyne? Disappearance of this. And we should have appearance. This has H's. So that should appear because these are carbon sp2H. Okay, nothing broad, nothing like that. Carbonyl stays. So this is present both in the reactant and the product. So that's not changed. It's not disappearing either. Here, that's another condition of a partial reduction of an alkyne. And this give me the trans alkene. But what do we see? This is going. And here we have these two H's are new. So that should appear and the other should disappear. So disappear the signal of the carbon-carbon double bond. So again, does not appearance of 1700. No, remember this is a carbonyl and it stays. So not appearing, not disappearing. Disappearing of the signal at 3100 appearance. I'm sorry, this will show because that is the alkene. So carbon sp2h, and that in disappearance of the alkene. So this is this. Okay, so that's how we monitor. So what really all you want to see is what you have at the beginning and what you have at the end, not really the mechanism in this type of question. So you're interested in the changes in functional group. You from an alkyne you get an alkene. That's what you want to see, and how you can explain that in terms of IR. Here, and this molecule, what are you doing? A hydrogenation. What is the functional group change? Well, the alkene is now being that unsaturation is disappearing, so that should disappear, and the double bond is mainly, that's the principal change, because so we see disappearance of no, that is disappearance, well, the carbon-carbon double bonds, that is close to, remember these is close to where the carbonyl is typically it's about 1680, 16 something, but nothing there that is like that, so I guess that's the closest. That will disappear. Okay, so now moving on.